Our next speaker also brings to a very current topic in the area of circularity, potentially reusing glass that has already had a service life in a building. So it's my pleasure to introduce Hans Ignacio Scholz from the TU Darmstadt and talk us through this subject. Thank you.
Thank you, Wim, for the brief introduction, and also thank you for your interest in our study, in our sustainability study with laminated safety glass. So I will tell you our work on laminated safety glass produced from reclaimed glass, insulated glass units. First of all, I will give you a brief introduction to our study, then our goals. And for that, I think it's good to go a step back and really see what's the definition of LSG and what the parameters of the bonding is, or the addition. And then I will go into our work with the test samples and how we also prepare them, and give you a brief outlook. First of all, sustainability is not a state secret. So we already heard that in the keynotes in the opening session that we have to work for a greener world. And in the float glass industry, 17 to 90% of the CO2 emissions come just from the float glass lines, from the float glass production. And in this case, for this study, because I don't want to bore you with everything, we have 80% of the CO2 emissions just come from the glass in the laminated safety glass. So that means that 60% just of it, like 20%, is from the other part of the lamination and the thin layers themselves. Also from the side of the politics, we have a need and we are obligated to give this a go, because we are already working towards the European Green Deal by reducing the net greenhouse emissions. And also we're looking forward the EU's Circularity Action Plan, where we have to implement functioning circular economy. In the case of our study, is a remanufacture strategy. The goal is to reclaim aged IGUs, separate them into its components, and then produce them into something new in the definition, something new for the component. And this is possible. So it is possible. This is state of art. But what about the quality? Do we meet today's standards? And what parameters should we look into? And this is where we have our study. And I want to take a step back and talk about the definition of laminated glass or laminated safety glass. No? Laminated glass, a composite of more glass panes that are bonded. And please, the word bonding is really important, by a polymeric interlayer or thin film. And for it to be classified as a safety glass, it has to have a post-breakage resistance. Okay, and the splitters doesn't have to hurt people. And they have to have a... Please come in. So, yes. For this, I talked about the word bonding. And bonding or addition is the general term for the bond strength between the interlayer in glass, where delamination resistance depends on its mechanic, temperature, and or humidity resistance. And this addition depends on the interlayer material, on the glass surface, on the production parameters, on the environmental conditions we put our products on, or the long-term durability. So we have a lot of parameters we have to take in account. So this makes, for working with reclaimed or remanufactured laminated glass, a big word. So where do we start? And our approach is all about the production. So if we take our production and we equal our laminating process, we just use the same interlayer, we use a glass without coating, we can do a big series where we can work with reference glasses. So we can produce LSG out of aged glass and produce LSG with a reference new glass the same way, and then we can have So we cut the parameters, the variables. What we didn't look into in this study is about the environmental conditions, because we didn't build the LSG somewhere, and about the long-term durability. But we used for our reference work the same interlayer material and the same production parameters. So we cleaned the glass the same way. We have uncoated glass for the H1 and the new one. So that leaves us with the parameters or variables, the roughness and the chemical composition of the glass surface. Yes, about our testing matrix, we did for this preliminary study first an extrema work. So we laminated the exposed positions of the IGUs, where we laminated or did samples, laminating position 1 with position 1, position 4 with position 4. And our position 1 was the thin side, our position 4 was in the production air side. So we did the reference glasses also the same, one by the thin side and one by lamination side on the air side and the lamination on the thin side. And the test we did through in this preliminary study is we tested the roughness of the glass surface. We did a bake test, or the known high temperature test, the humidity test, and we did also pummel tests. Now going into the samples themselves, we were lucky that we could reclaim a huge series of H glass for doing bigger series. This is a building in Frankfurt. The glasses are something around 33 years old. We were able to reclaim 67 of those. Sadly, we can just use 40 of them because in the process some got broken. But for this study, we had the chance, at least for the preliminary study, to use one of those. What we did is we cut the IGU, we separated it by a conservative process. We used a cutter for the secondary sealant, a cutter for the primary sealant. Then we recorded the surface damages or errors, if you want to tell them like that. We did a cut sheet where we prepared and defined which sample is going to go where for which test. And then we cut the samples. And lamination is a continuously cleaning process, so therefore we engraved an ID so that we can track our samples and see which one is which. Talking all about the cleaning process, for this study we cleaned the glass, or we produced the glass in the following way. We cleaned the panes with a glass cleaner, then with isopropanol, and following with distilled water. We use Crucible Ultra Clear 2 layers. And in our facilities, we have a vacuum autoclave, and we did the same procedure for each test sample. So that, or test batch, I would say. So we did the same for the H glass and reference glass that go to the bake test, for the H glass and reference glass that go to the humidity, and so on. So I will talk a bit about the roughness as a variable. The roughness is the average depth between a measured path. In this case, we did a linear path to see how the topography of the glass pane is. Why we do this? Because we said that's one of our variables. Interesting in our results is that from our H glass, the position 1 and position 4, as the thin side from our reference glass had the same, well, almost the same value, something 0.23 microns. And on the air side of the reference glass, we had a huge difference, like 5 times more. And it's something around 1 micron. At first I was like, oh, is this going to be a big influence? Oh, should I do not test these samples? But actually, it's a good evaluation, in my opinion, because now I can compare if the roughness plays a role. And just a hint why we put so much effort into the roughness. There is the German Association of Glass Structure Design that already published a study where the roughness was tested for the addition. And the higher the roughness, the worse the addition is. The smaller the roughness, then the better the hydrogen bonds or metal bonds in the case of the century air glass is. So, now, Now I will go to some of the testing, active testing. And we did for one batch the bake test or the high temperature test to determine if laminated safety glass can withstand the effects of high temperature over an extended period without a significant change. And we put these test samples 16 hours by 100 degrees Celsius, and after that we increase by 10 degrees an hour for testing also the limits. The good thing is that at 130 degrees, neither of the samples had new bubbles. So these small bubbles you see is about the production. That was my bad. But from 140 degrees on, we see new bubbles. So actually, I should have stopped at 140 degrees, but I wanted to be testing limits and to have something I can touch, I can see to compare the reference glass with the H glass. And we did that. So we scanned our results. We scanned the bubbles for all of the glasses. Of course, here you see the comparison of from my right side, the H glass, and my left side, the reference glass. And we written a script in Python, or a program, that counts out as the delamination area and the bubbles, so that we can really compare where this study is going on. And as you can see, these are our results. I will start with the reference glass. In the reference glass, we have almost the same delamination area, but with the H glass, we had once double so much delamination area and once like almost none. So what does this mean for us? First of all, it's a study with just 2 panes. 2 panes of the H glass, 2 panes of reference glass. We need a bigger series. For the position 4 test, same but different. We have with the reference glass, the good thing is that we have for the reference glass the same delamination area, so that means our laminates, in my opinion, are valid. And for the H glass, we have one sample that had the same delamination area and one that had so double to match. But here comes the big but, is that here I'm comparing also the roughness. And the roughness is compared to the H glass 5 times so much and has lesser delamination area. So we need to have a bigger study. So what does this roughness mean? Or we should go more into the chemistry and touch the surface composition of the glass. Analogically to the baking test, we did a humidity test where we put our test samples by 80% relative humidity and 50 degrees Celsius for 2 weeks to determine if the laminated safety glass can withstand the effects of humidity over an extended period of time and maybe have an occurrence of bubbles, delamination, cloudiness, or in this case, discoloration. What gladly didn't happen. So yay, our H glass passed the test. But always comes a but, because we're in research, we want to know what's happening here. If you can see in this test sample, you have a bit of discoloration and the glass corroded. So the position 4, I don't know why, position 1 didn't have that occurrence, had a corrosion degree. And of course, we told ourselves like, okay, let's go for it. Let's try also to quantitate it. But the problem here is that glass is transparent. It's really hard to do image processing or scan processing. And the contrast of the dots, corrosion dots, and the background is really similar. So we're still working on this. We hope that we can get like also a program by image processing to get also corrosion, but it's still on the work. But nonetheless, I was talking about quality and quality standards, and all samples passed that because the corrosion was not on the lamination side. It was on the outer side of the laminate. This for both of the positions and both reference samples, so good to go. Nonetheless, we need a bigger series. And last but not less important, we did a pummel test to determine the grade of mechanical adhesion within the glass surface and the thin film. And because we use a Kurai thin film, we also use the Kurai standards procedures for the pummel test. We cool the laminate at minus 18 degrees Celsius. In the case of the standards, you do it by 3 hours. I took a go and I did it for 36 hours because I wanted to have a homogeneous temperature for at least these preliminary tests. And here are results for the position 4 laminates. We achieved a pummel value of 5 compared to its higher. The highest value was 5 compared to the highest reference value, that is 8 from the reference new glass. And for the position 1, that is the environmentally exposed position, we had just a value of 1 less, so a difference of 1. So we have a value of 4, and the pummel standard of the reference class had the highest value of 7. Of course, I think this is a really hard test because the vision of the people is different. So it's really difficult to say, okay, for me it's a 7, maybe for you it's an 8, and stuff like that. So the evaluation was made by the naked eye, but of course we're now in times of digitalization, and we had a midterm goal to evaluate the test samples via image processing. So we can have, like, evaluate how the pattern is in the scans or the pictures, and then go through a program to say which value of the pummel these tests have. So, results, comparing tables. H-glass from position 1 compared to the reference glass, we have a big difference. So 4 to 7 or 3 to 6, a difference of 3. Here I will highlight also roughness, same roughness, okay? So this means, at least in this preliminary result, the chemical composition of the glass surface is playing a role. But for example, here also for the position 4, you can see we have here a glass which surface was something about 3 microns in the surface, like more than 10 times about the H-glass. And we see also a pummel difference. So we need to get into bigger series and also to have a better understanding what the surface properties mean for the addition of H-glass. So, as a summary, quality LSG with reclaimed, not reclaimed, with reclaimed glass is possible. We can meet the standards, but what does quality mean? So, what do we want to achieve? And this for, we need a bigger study, of course. So we're on baby steps. We need to develop better evaluation tools. We need to make a bigger test and study about topography in 3D or 2D and about the chemical composition of the glass. We will do bigger series with our partners, Everlam and Kurai, in this project. And of course, have an implementation of another test, a compressive shear test, to have a value like engineers like in megapascals or Newton per square area. Of course, thank you to our sponsors and partners, because with all of them, it's not possible. And thank you for your attention, and hopefully I could get you a good overview of our studies and a good interest to wake up what we want to achieve for the environment and our Earth. Thank you.